Chapter 1. You've heard the word functions. What is a function? How does it relate to an equation? Yes and no. Yes, because equations are just another way of writing functions. Again, it's in math class, it's much easier to write down the notes than trying to type them, because I'm gonna have formulas. So close your laptops. You don't need those, because again, you can't use a computer to take notes in a math class. In other words, equations are something like this. Y equals 3x plus 2. It's two-dimensional equation, where x is what kind of variable? Okay, I see I spent a lot of time studying over the weekend. I might just start having quizzes on the morning to make sure you all start looking at your notes. It's an independent variable, because it can be anything you want it to be. Throw it in there, and then you calc it out. Once you decide on the value for x, you get the value of y, which is what kind of variable? Dependent variable. So we have to decide on a value for x. Let's say it's 3. Then we got to plug it in there and work it out. Then we get our value. This value is actually, yes. A very good point. Yes. Typically, when we define dependent variable, we always say x and y, but you're right. Depending what you're solving for, that's what it becomes independent. So in other words, if I had x equals 3y plus 2, then y would be your independent variable. Yes, very, very good point. Yes, so it's whatever you're solving for. Whatever you're solving for is your dependent variable, because it depends on whatever's inside the equation. Very good. Very good question. So the difference between an equation and a function is the way it looks. Functions are defined by a letter. F, G, H, M, N, P. The only letters it can't be are the letters we use in the constant letters like E or X or Y. They can be anything else. And then, so this is the name of the function. Inside the parentheses, that's your independent variable. And then the equation. So the difference is this. Y is the same thing as a function. F of x is read the function f of variable x is. That's how you would read it. the function f of variable x equals some number, or some equation. We shorten it to f of x. This is the short script, right? So function name, variable name. So if I said g of heart, how would you write that? Whatever's after the word of is your variable, and whatever's first is the variable name. So in our example here, we would simply write like that. In other words, you define the variable value inside the function itself. So what this says, anywhere there's an x, you put a 3. So f of 3 equals 11. Now, let's look at the benefits of using function notation instead. Remember, these two pieces that you have actually represent a point. It's a location on a graph. So you have to look, where is it defined and what's your final answer, and plug them in there. In this format, you already know the x is what's inside the parentheses, and whatever's the answer is your y value. So that's one benefit of using function notation. Another one is, once a function is defined, it stays that way until it's redefined. So I could ask you this. Yeah, don't kick that trash can out. That's how I keep the door open. So put the trash can back in the door, please. So we see we have 3 functions that are defined here. So we'll go to the first one. F of 3 is, here's my function. So anywhere I see an x, I put a 3. I go to the G. Anywhere I see an x, I put a 1. And H, anywhere I see an x, I put a 4. You have to remember that each one of those functions are independent of each other. So now we go left to right. 2 times 3 is 6. Inside here, we have multiplication. Negative times positive is negative. 5 times 1 is 5. Four plus 2 is 6. inside the parentheses. So -5 minus 2, they're both negative. So the answer is negative. So we add the numbers. 5 plus 2 is 7. 6 divided by 3 is 2. Now we get rid of the parentheses. Positive and negative become what? Negative and a positive. So negative. Read left or right. Since 7 is bigger than 6, the answer is negative. 7 minus 6 is 1. They're both negative, so the answer is negative. So we add the numbers. And there's your answer. So you see, whenever you deal with functions, work the functions out independently. I work out each one of these independently, and then I'm just interested in combining where their values are in the equation. What if I give you this? That's supposed to be a g. So f of 0 minus g of -1 over h of 4. Okay, so we look at what is f of 0. So it's 2 times 0 minus -5 times -1 minus 2. 4 plus 2. Because these F, G, and H are still defined up above. So the first parenthesis, 2 times 0 is 0. Negative times negative is positive. 5 times 1 is 5. Minus 2. 6 over 3. So 0 is nothing. 5 minus 2 is 3. 6 over 3 is 2. And there's your answer. So that's the beauty of functions. Because if I didn't use functions, then I'd have to write the equations in each one of those spaces and say x is this one for the first one, x is, it's just very horrible. All right. And we'll be using function notation pretty much for the rest of the semester. Just remember that the function is equal to the value y. Once you know that, then that helps you in graphing also. or whatever function name. It's just a function equals the y value. All right, let's discuss how the independent and dependent variable are related. The relationship between the independent and dependent variable. We're going to use two words. Remember, mathematicians are not too ingenious when naming things. Have you ever heard what they called mail when you deliver mail in the old days? What was that called? What's that? Postal? What's nothing? They called it what? Whenever you're sending a letter to each other. Well, yes, mailing, yes. It was actually called correspondence. Actually, that's what they used to call distance learning back then. Before we had internet and stuff, people used to sign up for a school. The school would send them the textbook and some homework. They send it back. So you would be a correspondence learning. Then they said distance learning. Then they used radios and they used TVs and they get computers. But they used to be called correspondence learning. A correspondence. Now, remember, think of this as letters. Person A sends a correspondent. Can that person send it to more than one person? The same letter to more than one person? Now, they can send a copy of it, but you can only receive one letter from one person. That's a correspondence. So a correspondence, when it comes to mathematics, we called the sender, the beginning, we call that the domain. And the person or the entity it's sent it to is called the range. What variable belongs in the domain? So this is the X variable and the range. So what it says is each value of X maps. We call when we do this little arrow there, that's called maps. When each value of X maps to one and only one member of Y, or one-to-one member of Y, one-to-one Y. That's a correspondence. So let's look at our first example here. Is this a correspondence? Yeah. Well, here's the X, here's the Y. Yeah, so this is a correspondence because each person here sends to only one person here. In other words, are there two arrows coming out of any of these? No. Yeah, these guys, I mean, all these could be sending it to the same person. Think of a classroom. These are the students, these are the instructors. So all the students can be sent to one instructor. So that's a correspondence. How that relates now to whole function things. How about this one? No, why? Jefferson has Breyer and Ginsburg. Yeah, so you can't have split letters. So that's not a correspondence. Why is it important? Correspondent equation, when you do have it's correspondent, then it is a function. So if the relationship between the x and y is a correspondence, then that means the function that it is a function. Now, what does that mean? Each value of x maps to one and only one value of y. Graphically, how can we prove that if something is not a correlation, a correspondence, I mean? If there's what?
Then you go back to the potential. So like the potential one, since there's one x going to two different y's, that's going to create a vertical line in the graph, and so you can't.
Yes, very good. You remember that from your earlier math classes. It's called the vertical line test. How many of y'all remember that? Oh, good. So, yes. If you can draw a vertical line through any graph and it crosses it more than once, if a vertical line crosses the graph of an equation, vertical line crossing equation more than once, then it is not a function. If a vertical line crosses the graph of an equation more than once, it is not a function. Remember, it has to be a correspondence. For this x, it belongs to this y, and it also belongs to this y. So each x can only have one y that it goes to be a function. Since this one has more than one, it's not a function. It's not a correspondence. In that case, if it's not a correspondence, it possibly may be a relation. What is a relation? A relation takes the correspondence one step further. When the x values can map to two or more y values. Why is it two or more? Because if it was one, it would be a correspondence. Can it be zero? It could be zero. What if I had this? If my function 1 over x. Are there any x's I cannot use? Which one? Which x can I not use? X cannot equal 0. I can use anything else except 0. Because we have these two possibilities. Actually, any number on top of 0 is what? Undefined. Actually, it's infinity. That's why it's undefined. 0 over 1, or 0 over any number, is 0. And it simply goes down to if you were to use words to explain it. For example, we have 4 over 2. What is that statement really asking you? 4 divided by 2. But what is it asking you, though? It's how many times does 2 go into 4? That's what it's asking you. How many times does 0 go into 1? Infinite number of ways. I can keep on putting nothing into your bank forever. So if you work for me, that's what you get. But if you had, how many times does 1 go into 0? 0 times. It doesn't fit in there at all. So let's look at example 3. This is example 3, and it's asking, determine whether each of the following relations is a function, identify a domain and range. Down. What's that? Last week. I had them on the table back there. But yeah, I'll bring some more next time. And what I'll also do is from now on, at the beginning of each chapter, I'll send all of them out to you via remind, so you'll have them. Yeah, I'm sorry. Who does not have a copy of the examples? You guys were here last week.
Oh, wait. I got that. Yeah.
Didn't I put the whole entire chapter out there? Oh, okay, I'm sorry then, because I thought it was my other class then, because I thought normally what I do then is I will start, when we start chapter 3, I'll have all of the chapter 3 examples on there, so we'll have one packet. Okay, I'm sorry, but yeah, so I'll send you this today. Example 3. I am so sorry. I don't know where my head is. Okay, here we have now it's asking you, is the following relation a correspondent, or is it a function? So, is it a function? Yes or no? Then set the domain and tell me the range. So who thinks this is it's a function? Who thinks it's not a function? Why? Right, because there's the same x's go to different y's. If you have the same x, it has to have the same y. So not a function. So the domain, what's the domain? Yeah, 9 and 2, or 2 and 9. It's actually supposed to be a list of numbers, but I have a hard time writing those little squiggly brackets. What's the range? Very good. -2, 5, 5, 7, 0, 1, 4, -2. Is this a function? Yes, because if each of the x values are different, it's automatically a function. Because if each of the x values are different, then there's no way they can have the same x value. What's the domain? Put them in decreasing order. So it's all the first numbers. And the range, it's all the second numbers. So it's domain range. Yes or no?
Yes.
Yeah, because all the x's are different. Yes, it is a function. All x's are different. The domain, -5, 0, and 6. And the range, 3. Function or not? Ooh, got a smackdown. Yes, it is. Here's -2, and here's -2. Are they the same y values? So it's the same point. Same with the threes. They're both threes, and they're both. If the x values are the same, the y values better be the same. It's the same point. So yes, this is a function. Trick question. And the domain, -2, 3. Range, anybody not see all that? So is it a function? Yes. Example 4. Here's a function. F of x equals 2x squared minus x plus 3. Find the following. That's supposed to be a minus 4 back there. So go ahead and try to work these out. So this one tells us anywhere C and X, put a 0. So we have 2 times 0 squared minus 0 plus 3. That's 0, that's 0, so it equals 3. So what's this number called here? It is a solution, but in this context here. It's the y-intercept, because remember y-intercept, you set x equal to 0. Whatever you get there is your y-intercept. So the y-intercept is at 0, 3. The y-intercept is always the constant number of a function. Okay, now I put -7 in there. So -7 squared. -7 times -7 is positive 49. Very good. Negative times negative is a positive. 2 times 49. Very good. And we can go ahead and since these are all addition, we can group them by associativity however we want. So +7, +3 is +10. 98 plus 10, 108. So far, so good. Two times 5a squared minus 5a plus 3. So what is 5a squared? Yeah, 5a squared. The square means take whatever's under it. This is called the base. This is called the exponent. It says multiply it to itself twice. So 5 times 5 is 25. A times a is a squared. So it's 25a squared. The negative times positive is a negative 5a plus 3. Now we have to get rid of this parenthesis. So 2 times 25, 50a squared minus 5a plus 3. That's as far as we can go. Why? Not like terms. It's apples and oranges. A squared, that's a, you can't combine them. Now I gave the least room for the biggest one. So this one says 2 times a minus 4 squared minus a minus 4 plus 3. So a minus 4 squared means a minus 4 times a minus 4. Again, we haven't talked about distributivity property in the binomial sense, but y'all have heard of FOIL technique. So everything in this first parenthesis has to multiply to everything in second. So a times a squared. Positive times negative is negative. A times 4 is 4a. So that's for that one. So negative times positive is negative. 4 times a is 4a. Negative times negative is positive. 4 times 4 is 16. Whenever you get rid of parentheses, the first thing you do afterwards is combine like terms. So here we have like terms, 4a, 4a. So we get a squared. They're both negative. 4 plus 4 is 8a plus 16. Remember, if the signs are the same, since they have the same terms, we just add the coefficients. So we have 2 times a squared minus 8a plus 16 minus a minus 4 plus 3. So now what do we do? Can we do anything inside the parentheses? No. So we have to get rid of the parentheses. Distribute. This 2 multiplies to everybody inside the first one. So 2 times a squared is 2a squared. Positive times negative is negative. 2 times 8 is 16. Positive and positive is positive. 2 times 16, 32. Negative times positive is negative a. Negative times negative is positive 4. So we got rid of the parentheses. Remember, once you get rid of parentheses, next step is always what? Combine like terms. So start with the highest exponent. So we have 2a squares. That's gone. Now let's look at the a's. We have negative 16, negative 1. They're both negative, so I add them. 16 plus 1 is 17a. So that's those 2 gone. 32 plus 4, 36 plus 3, and they're all positive, so it's positive 39. You've seen this stuff before, and you've slept since then, so I've got to refresh it. Any questions about those? Let's work backwards. I give you the function, the graph. This is of f of x. I'm asking you here, what is f of negative 3? And what is f of 1? I even give you the function. X squared minus 6. Without calculating, without using any addition and subtraction, only using the graph, tell me the answers here. That's why I shouldn't have given you the equation. What is this asking us? What is it telling us? X is negative 3. So let's go at negative 3. Let's go till we find the function. And then find the y value. So the answer is 3. And if we plug it in there, negative 3 squared is what? 9 minus 6? 3. So do the same thing here. When x is 1, go from 1 to where the graph is. And then we're looking for the y value. So it's negative 5. You know, if you have the graph, you don't need the function. The graph tells you everything you need to know. What are my x-intercepts? Let's pretend they're halfway between there. So what are they? Nope. Nope. We talked about it last week.
Five, 0, other numbers. Is that to -2?
Right.
Parentheses, -2.
Right. It's a location. You have to give me the coordinates of the location. Very good. And since it's the x-intercept, I don't want the y values. I'd make them equal 0. And what's the y-intercept? Zero, -6, right? Because it doesn't go anywhere horizontally, it goes straight down, -6. Is that a function? Why? Very good, very good. It passes the vertical line test. Anywhere I draw a vertical line, it crosses it only once. So it is a function because it passes the vertical line test. Is that a function? No, because practically anywhere it crosses it more than once. So not a function. Okay, these are going to be easy. Which of these are functions? Is A? Yes. No, this one's not a function because it fails. Is this?
No.
Nope, fails. This one?
No.
Is this one?
Yes.
And this one?
Yes.
Yes. Even here, because this one's a closed circle, this is an open circle. What does a closed circle mean? It can be included in there. Open circle means not included. So at -1, it's going to be up here. It's going to be 1. So far, so good. So now let's look at finding the domain and range of a function. Well, no, we'll do the range later. Finding the domain of a function. Let's do it step by step. Do the range later. So if I gave you this function, first off, is it a function on the entire domain? In other words, are there any x's I cannot use? Zero minus 3 is -3, so that's doesn't give me anything. Very good. If you ever have a fraction, set the denominator equal to 0. And solve for x. Any x you get there, you cannot use. So x minus 3 equals 0. Add 3 to both sides. So x, the only x I cannot use is 3. So what's my domain? Does it matter if the top is 0? No, because if the top is 0, then that's just a 0. That's the intercept. That's the x-intercept. But now, since I cannot use 3, what's my domain? Think about it. My domain can be anything from -infinity to positive infinity. That's what we call all real numbers. I'll use this symbol when I talk about all real numbers. But I can't use I cannot use 3. So what's my domain? Very good. So I can use everything on this side. So I can use everything from negative infinity to 3. I just can't use 3. And then I can use everything over here from 3 to positive infinity. And since there are two different sides, I use the or statement, the union, which means or. So my X value can be in here, or it could be in here. It just cannot equal 3. So is that valid? Is 1 in the domain? Yes. Because that's going to give you 1 over -2, which is -1 over 2. How about if I gave you this? No, because here we decided we can't use 3. No. Because if we do that, we get 0 on the bottom, and that's not good. Okay, we'll look at the second one. G of x is equal to radical x plus 5. So looking at the equation, are there any x's you can tell me that you can't use automatically? There's only 3 types: positives, negatives, and zeros. So we have negative. Can you use negatives in this function? Why not? What's that? That's a good answer so far. Yes. I cannot use these, and I'll show you why in a second. How about 0? What's the square root of 0? I can use 0. How about positive numbers? Now, the reason you can't use negatives, actually, this is actually an nth root. This is called the root. The root tells us the number of times a value must be repeated to take it out. Of the radical. So if there's nothing there, the root is 2. It's a square root, 2. Which is why the square root of 4 is made up of 2 times 2. Since it happens 2 times in there, I can take it out. And there's nothing left inside the radical, so it disappears. The square root of 25. 25 is made up of 5 times 5. There's an invisible number there. It's a 2. This happens twice, so I could take it outside. There's nothing in there, so the answer is 5. Because 5 times 5 equals 25. So give me two numbers, they have to be identical, that equal -4 when I multiply them together. No, so you can't, because you can't put -2 in there. Right, so yeah, -2 times -2 is a +4. So that's why you can't use negative numbers. So the domain of radicals is 0 to infinity. That's the domain of radicals. So this is true as long as our root is even. If you have an even root, you cannot have a negative inside there. But if the root is odd, -8 is made up of -2, -2, -2. They're all the same. There's 3 of a kind. So the answer is -2. So if the root is odd, then you can have a positive, negative, or 0. So the domain of an odd root is -infinity to +infinity, or all real numbers. Again, see, we haven't talked about radicals or anything like that yet. That comes at the end of this, or pretty much the next 2 sections. And we're gonna go through all those. So at the end of chapter 1, I'm gonna want you, one thing I want you to know is be able to look at a function and be able to tell me how many solutions it's gonna have, what's the shape of the graph gonna look like, what direction does it open up, what direction is it going? That's called end behavior. We'll do that in the next couple of sections. Does this 5 add anything to it? Into the domain? Nope. The domain deals with X. So the 5 doesn't do anything. Example 9. Here's my function. Tell me the domain of these functions. We can't do H. We can't do this one yet. We can do C. There. Tell me the domain of each of these. So for A, we have a fraction, a rational expression. What's the only thing we cannot have here? Yeah, we cannot have 0 on the bottom. Set it equal to 0. So the only thing x cannot be is 7. So my domain is negative infinity to 7, 7 to positive infinity. Let's see. We haven't talked about this one yet. X cubed. Are there any rules about x cubed? Can x be positive? Can x be 0? Can x be negative? Yeah, so this one has no restrictions. How about inside here? Can you put a negative number in there? You were going to say no. Yeah, because absolute value of -2 is 2. The absolute value tells you the distance of how far that number is from 0. -2 is 2 units away from 0. Can it be 0? Yeah, there is no movement. Yeah. Can it be positive? Yes. So this one is all real numbers. Or from negative infinity to positive infinity. Now the last one. What are the restrictions on this one? Can inside there be positive? Can it be 0? Can it be negative? Yeah, this one is all real numbers also. Because it's an odd power root. The domain for an odd power root, third root, fifth root, seventh root, is all real numbers. And if not next class, then the class after, we'll look at the graphs of all these. So it makes more sense. Actually, we'll do it next class, so we'll have more idea what this is all talking about. Oh. Look at this graph here. What's the domain and range of this graph? Why? Mm-hmm. Right. Domain, look at the x values. These graphs have arrows on both sides, so they're going to go infinitely to negative infinity. But they're going slowly away. So the domain is from negative infinity to positive infinity. What's the range? From negative infinity to 4. Or you can say for this one, this is the range is y is less than equal to 4. Or you can say from negative infinity to 4. This is bracket because it is a solid dot there. So what's the domain and range here?
Isn't the domain -4 to 3?
Yeah. So look at the both ends. The domain, since that's a solid dot, it's a bracket. And it stops at 3 and it's an open. So we can't use it. Or we can say -4. We can put an equation. What's the range? Well, everything's in there also. So no, the range is only where it starts and where it stops. Always start with a smaller number. You can't use 2 because it's an open circle. And that's a closed circle, so you can use 6. So parenthesis means you cannot use, bracket means you can use. Again, we'll cover all that at the end of this chapter, which is, I don't know why they threw it in there. Okay, now we have some graphing to do. Graph these. One over 2x plus 1. Hold off on these because until we talk about the structures of functions, you really can't tell these things until you just look at them. Can you tell me the domain? All real numbers. What kind of equation is this? Why is it linear? There's no special operations. There's no square roots, no absolute values, no exponents. So it's linear. Linear equations by definition are all real numbers for domain and range. How about this one? What's the domain? What's the range here? Yeah, again, let's do this and then we'll call it a day. Because the rest of these really mean nothing until we know what the functions really look like. Well, you cannot have negatives inside there, right? So the smallest you can have in there is 0. So take that equation, whatever's inside there, set it equal to 0. So that means we subtract 4. So x equals -4. That's the smallest you can put in there. So the domain is from -4 to infinity. The range are the y values. So if -4 goes in there, what's the smallest it can get? 0. And then what's the highest it can go? And we're going to see next time that this graph looks like this. So once I show you the graphs next time, then all these will make more sense and it'd be easier for us to decipher the domains and ranges. Okay, and I'll give you all copies of all these next time. Yeah, there's a whole bunch of stuff next time. All right, everybody, have a great day. See you next time.